Welcome to True Projects. In this video, we are going to explain about the project title RockNet, Rockfall and Earthquake Detection and Association via Multitask Learning and Transfer Learning. Before diving into the execution, let me give you an overview of the project. Natural hazards are events that happen naturally and can be dangerous to people and things around them. Rockfalls are when rocks fall from steep areas like mountains and can hurt people or damage buildings. Earthquakes are when the ground shakes suddenly and can make buildings collapse or cause things to fall down. Both of these events can be really scary and can cause a lot of damage, so it's important to know about them and be prepared in case they happen. Imagine living in an area where rockfalls and earthquakes are frequent. These natural events can be dangerous, causing harm to people and damage to buildings. The project aims to build a smart system that can quickly and accurately detect when these events are happening. By spotting them early, we can warn people to stay safe, help emergency responders react faster, and even plan how to reduce the damage they cause. So, this project isn't just about knowing when rockfalls and earthquakes occur, it's about keeping everyone safe and minimizing the impact of these hazards on our lives and surroundings. Traditional methods for rockfall and earthquake detection involve manual observation by experts, seismic sensors, or specialized detection algorithms. However, these methods can suffer from drawbacks like high false alarm rates, limited scalability, and reliance on expert interpretation, leading to delays in response time. In the base paper, the author proposes RockNet, a deep learning based multitask model tailored for detecting rockfall and earthquake events within local seismic networks. It comprises two submodels, a single station model for computing waveform mask and earthquake phase identification, and an association model for determining local seismic event occurrences. RockNet enhances event detection and classification accuracy, thus contributing to the improvement of early warning systems and disaster response strategies. To improve rockfall and earthquake detection, we have proposed a voting classifier that combines the strengths of K nearest neighbor KNN and random forest algorithms. KNN looks at the nearby points to classify, while random forest combines many decision trees for accuracy. By blending their predictions, our classifier becomes more robust, accurately spotting seismic events. This enhances disaster readiness by providing reliable detection crucial for prompt response and mitigation. The project's outcomes benefit emergency responders, civil protection agencies, geological survey organizations, and communities in high risk areas prone to rockfalls and earthquakes. With a reliable detection system, timely warnings can be issued, enhancing disaster preparedness and potentially saving lives while safeguarding infrastructure. This system's effectiveness lies in its ability to quickly identify hazards, allowing for prompt responses and mitigation measures, ultimately reducing the impact of these natural events on communities and infrastructure. Moving on to front end integration, in this project, we have used Flask to build the front end. Flask, a lightweight Python web framework, is incorporated into the project to create a user friendly interface. It manages user authentication through SQLite3 database, enabling sign up and sign in functionalities. Users can input analysis values via Flask, which routes requests to the backend for processing and prediction. This integration enhances the project's accessibility via web browsers, making it more user friendly and accessible to a wider audience. To implement this project, we need software and hardware requirements. Software requirements of the project are application is Anaconda, primary language is Python, front end framework is Flask, Backend framework is Jupyter Notebook. Database is SQLite 3. Front-end technologies used in the project are HTML, CSS, JavaScript, and Bootstrap 4. Hardware requirements of the project are operating system of Windows, processor of Wi-Fi and above, RAM of 8 GB and above, hard disk of 25 GB and above. Algorithms used. These are the algorithms proposed in the base paper by the author, which are RockNet, SVM support vector machine, KNN, K nearest neighbor, and random forest. And here, this is the algorithm which we have proposed to further improve the performance. We have built all these algorithms to compare the performance with different evaluation metrics like accuracy, precision, recall, and FN score. And here, the voting classifier outperformed the other models, and that is the reason we have deployed it in the front end. So let me explain you what voting classifier is. A voting classifier is an ensemble learning method that combines predictions from multiple individual classifiers to make a final decision. It aggregates the predictions to produce a single, more accurate outcome than any individual classifier could achieve alone. In the project, the voting classifier aggregates the predictions from both KNN, K nearest neighbor, and random forest algorithms. KNN makes predictions based on the majority class among its nearest neighbors, while random forest utilizes ensemble learning to improve accuracy and reduce overfitting. By merging the predictions of these complementary algorithms, the voting classifier strengthens the system's ability to accurately identify and associate seismic events, ultimately enhancing disaster preparedness and response efforts through more reliable event detection. Now, let us execute this project. To execute this project, first we need to open the code folder which contains the project source code files. So here, this is the static folder. This folder consists of files related to CSS, JavaScript, and Bootstrap. This is the templates folder. This folder contains all the HTML pages used in the project. It includes files like index.html, about.html, and more, which represent different pages of the website. This is app.py file. This .py file contains the information related to front-end logic. It includes code written in Python that handles server-side operations such as processing user requests, interacting with the database, and generating dynamic content to be rendered in the HTML templates. And here, this is the model folder which contains algorithm information which will be loaded into the project code during runtime. This is notebook.ipynb file. This is a Jupyter notebook file which contains a combination of code, graphs, and outputs all in one place. It allows users to write and execute code in individual cells, making it a popular choice for data science. This is signup.db file. This file is the database file used to user information. And here, this is the dataset file. Let us open this. So here, these are the parameters which represent key attributes associated with seismic events, including earthquakes and rockfalls, and are pivotal for analysis and detection purposes within the project. They encompass details such as time, latitude, longitude, depth, magnitude, and associated uncertainties and metadata. So, this data set will be used to train the models. And here, this is the target column, which represents the different types of hazards, natural hazards. Now let us close this data. And here, this is the test cases file. Let us open it. So this is the sample data set which we will use during the execution. So here these are the parameters which are latitude, longitude, depth, magnitude type, net. And here this is the target column in which we have the different types of natural hazards. So here 0 means earthquake is detected, 1 means rockfall is detected, and 2 means noise is detected. So These are the test cases which we will use during the execution. Now let us close this. First, we need to copy the path of the code folder from the address bar of the File Explorer. So here I'm copying the path. Now open the Anaconda prompt. Use the cd command followed by a space and paste the copied path and hit enter. This command is used to change the current directory to the code folder's path. Compile the app.py file using the command python space app.py. So here I'm typing python space app.py and hit enter. This command will execute the Python script and perform a runtime check for any syntax errors or logical issues. After running the app.py file, the Flask framework will host the application locally at the default address localhost, which is this, and port, which is this. Now copy this local link provided by the Flask framework. I'm copying the link and paste this copied link into any web browser. I usually prefer Google Chrome and hit enter. The homepage of the project is displayed in the browser. This is the front end built using Flask framework. If we are new users, we need to register first. So click on sign up link here. So here we need to enter all these details to register. But I have already registered. So click on sign in. So here we need to enter the username and the password, which are static, and then click on sign in. We have signed in successfully and we are redirected to the prediction page. So here we need to enter these parameters for the detection. Before entering the parameters, let us understand the parameters. So the first one is latitude. Latitude represents the geographical position of the seismic event on the Earth's surface, measured in degrees north or south of the equator. It helps locate where the earthquake or rockfall occurred. Coming to the next parameter, which is longitude. Longitude indicates the geographical position of the seismic event on the Earth's surface, measured in degrees east or west of the prime meridian. Together with latitude, it provides the precise location of the event. Coming to the next one, which is depth. Depth signifies the distance below the Earth's surface where the seismic event originated, measured in kilometers. It helps determine the earthquake's focal depth or the depth of the rockfall occurrence. Magnitude. Mag refers to the magnitude of the seismic event, representing its size or energy release. It quantifies the strength of the earthquake or the intensity of the rockfall event. Coming to the next one, which is mag type. Mag type specifies the type of magnitude measurement used to determine the seismic event's magnitude, such as ml for local magnitude or mw for movement magnitude. It indicates the methodology employed to calculate the earthquake's magnitude. Coming to the next parameter, which is net. Net denotes the seismic network associated with reporting the seismic event. It identifies the network of seismic stations or data sources used to detect and monitor the earthquake or rockfall event. Now let us enter the values for these parameters from the test cases. So here, these are the test cases which I have showed you during the execution. So from here, let us enter the values. So the latitude is minus 6.5986. Longitude is 132.0763. Depth is 38.615. Magnitude is 6.1. Magnitude type is 15. Net is 12. And here we can see that the target is 0. 0 means earthquake is detected. So here I have entered the values. Now click on Click here. And here we can see results for the given input is earthquake detected. So we can see a earthquake is detected based on the entered values. Now let us enter another set of parameters. Click on home link here. So again, from the test cases, let us enter these values. Latitude is 41.527. Longitude is 88.71. Depth is 0. Magnitude is 5.8. Magnitude type is 4. Net is 12. Now click here. So here we can see result for the given input is noise detected. So here we can see based on the entered values, noise is detected. Now let us enter on the set of parameters. Click on home link here. So again, from the test cases, let us enter these values. Latitude is minus 21.823. Longitude is minus 139.048. Depth is 0. Magnitude is 5.7. Magnitude type is 4. Net is 12. So here I have entered all these values. Now click here. So here we can see the result for the given input is rockfall detected. So here we can see rockfall is detected. Now click on home link again. Let us enter another set of parameters. So here the latitude is 41.657. Longitude is 88.69. Depth is 0. Magnitude is 5.9. Magnitude type is 4. And net is 12. So I have entered all the values. Now click here. And here we can see the result that noise is detected. In this way, just by entering the parameters related to seismic events, we can detect different kinds of seismic events, which are earthquake, rockfall, or noise. Now click on graph link here. So here this is the comparison graphs for all the models. So here we can see blue color represents accuracy, orange color represents precision, green color represents recall, and red color represents FN score. So here on the x-axis we have the algorithm name, and on the y-axis we have the scores for all the evaluation metrics. And here this is the accuracy comparison graph. Here on the x-axis, we have the algorithm name, and on the y-axis, we have accuracy score. Accuracy is a measure of how well a model correctly predicts outcomes. It represents the proportion of correctly classified instances among all instances evaluated. This is precision comparison graph. Here on the x-axis, we have algorithm name, and on the y-axis, we have precision score. Precision is a measure of the correctness of positive predictions made by a classifier. This is recall comparison graph. Here on the x-axis, we have algorithm name, and on the y-axis, we have recall score. Recall is a measure of the classifier's ability to correctly identify all relevant instances from a dataset. And here, this is the FN comparison graph. Here on the x-axis, we have algorithm name, and on the y-axis, we have FN score. FN score combines precision and recall into a single value. It provides a balance between precision and recall, taking into account both false positives and false negatives. So the algorithm which is performing best will be used for prediction. So in this project, The voting classifier outperformed the other algorithms, and that is the reason we have deployed it in the front end. Now click on sign out link here. We have developed a robust system for detecting earthquakes and rock falls using the RockNet model. Additionally, we have employed a voting classifier as an extension seamlessly integrated into Flask. By inputting parameters associated with seismic events such as earthquakes and rock falls, our system accurately detects and associates these events, aiding in disaster preparedness and response efforts.
Thank you for watching video. For more projects, please visit our website www.trueprojects.in. For updates on latest project videos, please visit True Projects YouTube channel and subscribe.